In this video, I will show you an AC circuit example in which we will reduce the entire network to a Thevenin equivalent circuit and a Norton equivalent circuit. As the Thevenin and Norton equivalent circuits are dual of each other, that means if I can draw Thevenin equivalent circuit, I can easily draw the Norton equivalent circuit, or if I can draw the Norton equivalent circuit, I can easily replace that with a Thevenin equivalent circuit. Okay, see, draw the Thevenin and Norton equivalent circuit of the following circuit across A and B terminals. I have to draw the Thevenin and Norton equivalent circuit across these A and B terminals. Thevenin theorem states that if I have two terminals, let's say A and B terminals, and within these A and B terminals we have a very big network, we can reduce the entire network to a single voltage source in series with an impedance, and that network will be known as Thevenin equivalent circuit. That means our entire network will be reduced to a single voltage source VTH and an impedance ZTH in series with that VTH. Then this circuit will be known as Thevenin equivalent circuit. And Norton theorem states that if within A and B terminals we have a very big network, we can reduce that network to a single current source in parallel with an impedance ZN between those two terminals. That current source will be known as Norton current source, and the impedance will be known as Norton impedance. Within A and B terminals, and that will be the Norton equivalent circuit of that network. Okay, see, this is our Thevenin equivalent circuit and this is our Norton equivalent circuit, and Thevenin and Norton equivalent circuits are dual of each other. That means if I can draw Thevenin equivalent circuit of any network, I can easily draw the Norton equivalent circuit, or if I can draw the Norton equivalent circuit of any network, I can easily convert that into Thevenin equivalent circuit. How does we do that? We do that by using source transformation theorem. See, between this A and B terminals we have this voltage source connected in series with the impedance ZTH. Here the value of ZTH will be exactly same. Thevenin impedance will be equal to the Norton impedance. Now see, if I know the value of VTH and ZTH, I will calculate Norton current IN equal to VTH divided by ZTH or ZN. Or if I know the value of Norton current, I can easily calculate Thevenin voltage IN into ZN or IN into ZTH. So whenever we have to draw Thevenin or Norton equivalent circuit of any network, if I can draw Thevenin equivalent circuit, I can easily convert that into Norton equivalent circuit. Therefore, I don't have to know both Thevenin and Norton theorem. I will simply proceed with Thevenin equivalent circuit, and after drawing the Thevenin equivalent circuit, I will draw Norton equivalent circuit from that. Okay, draw the Thevenin and Norton equivalent circuit across the A and B terminals. See, we have to draw the Thevenin equivalent circuit across this A and B terminals, and across this A and B terminals we have this load impedance ZL connected. To draw the Thevenin and Norton equivalent circuit, at first I will remove this load impedance ZL. After that I will calculate Thevenin impedance ZTH, which is equal to Norton impedance ZN. After that I will calculate Thevenin voltage VTH. After calculating VTH, I will take VTH equal to Norton current IN and Thevenin impedance ZTH. So if I divide VTH, Thevenin voltage, with the Norton or Thevenin impedance, I will get our Norton current. So let me remove this load impedance. With respect to A and B terminals, if I remove the load impedance ZL, the remaining two terminals network will look like this. Now see, with respect to these A and B terminals, I have to calculate Thevenin impedance ZTH and the Norton current IN and the Thevenin voltage VTH. So at first I will calculate Thevenin impedance. In that case, I will replace this voltage source with a short circuit and this current source with an open circuit. If I replace this current source with an open circuit, that means I will remove this current source from our original network, and if I replace this voltage source with a short circuit, I will disconnect this voltage source and connect the two terminals with a short circuit. So for ZTH calculation, our circuit will look like this. See here, I have removed the current source. That means I have replaced the current source with an open circuit and the voltage source with a short circuit. Here we have to calculate ZTH with respect to A and B terminals. See, if this is our B terminal, you will see I can continue this B point up to this point. As this is an open circuit, I can disconnect this portion from the network. So see, with respect to this A and B terminals, I have this impedance, I have the resistance 4 ohm and this J2. If I call their branch impedance as Z1, you will see Z1 will be equal to 4 plus J2. This branch impedance will be equal to 4 plus J2. Now look, between this B and A terminals, you will see this 8 ohm resistance, 1 ohm resistance and this capacitance whose capacitive reactance is equal to minus J3. They are connected in series. If I denote their branch impedance with Z2, what will be the branch impedance of this? Z2 will be equal to 8 plus 1 minus J2 minus J3. So this will be equal to 9 minus J3. Now look, between this A and B terminals, the impedance Z1, which is the impedance of this branch, and the impedance Z2, which is the impedance of this branch, Z1 and Z2, they are connected in parallel, and their equivalent parallel impedance will give us the Thevenin impedance of this circuit. So here our ZTH will be equal to Z1 into Z2 divided by Z1 plus Z2. Z1 will be equal to 4 plus J2, and what will be Z2? 9 minus J3 divided by 4 plus J2 plus 9 minus J3. Now see, ZTH will be equal to 3.175 plus J 0.705. This will be equal to 3.25. Phase angle will be equal to 12.53 degree. So this is our Thevenin impedance ZTH. Thevenin impedance is equal to Norton impedance. Okay, so here our Thevenin impedance ZTH is equal to 3.18 plus J 0.705 ohm. Okay, now see, we have to calculate VTH with respect to A and B terminals. Whenever we have to calculate VTH, some may prefer mesh analysis or nodal analysis to calculate this VTH, but you have to understand that while we will use mesh or nodal analysis, we have to solve some simultaneous linear equations, which is very difficult to solve in case of complex numbers. Therefore, I will use superposition principle to calculate VTH rather than mesh or nodal analysis, to avoid the complexity of solving simultaneous linear equation. So here we have two energy sources, 20 phase angle 0 degree voltage source and 4 phase angle minus 90 degree current source. So at first I will keep this 20 volt voltage source active. In that case I will replace this current source with an open circuit. So our circuit will look like this. See, I have removed the current source or replaced the current source with an open circuit, VTH. In that case, I will denote the voltage between this terminal to this terminal with VTH prime. Now see, at first you have to understand the direction of current flow in the circuit to calculate this VTH prime. See here, if this is its positive terminal and this is its negative terminal, you will see, let's say, for the sake of argument, the source is supplying a current of I. It will divide into two portions. One will go in this direction, another will go into this direction, and this current will return to this point through this path, and this current will get into this point by this path. Now see, when the two currents will get into this point, the total current I cannot complete its path. Therefore, in the circuit, total current I will be 0, and you know that the total impedance of this branch Z2 is equal to 9 minus J3, and the total impedance of this branch Z1 is equal to 4 plus J2. As the total current I is 0, so current in this direction will be 0 and current in this direction will also be 0. Therefore, IZ1 will be equal to 0. Sorry, I1Z1 will be equal to 0 and I2Z2 will also be equal to 0. So you will see there will be no voltage drop from this point to this point. Therefore, you will see this 20 phase angle 0 degree, this voltage will appear across this A and B terminals. Exactly we have in this source 20 phase angle 0 degree, with this side positive and this side negative. The voltage source will maintain its polarity here, this side positive and this side negative. So VTH prime is equal to 20 phase angle 0 degree. So here VTH prime was equal to 20 phase angle 0 degree volt. Okay, after that I will keep this 4 phase angle 90 degree ampere current source active. In that case, I will replace this voltage source with a short circuit. If I replace the voltage source with a short circuit, our new circuit will look like this. This is the current source of 4 phase angle 90 degree. This was our resistance of 8 ohm. This was our resistance of 1 ohm. This was our capacitor whose capacitive reactance was minus J3. This was the resistance of 4 ohm. This was the inductance of J2. This is our A terminal and this is our B terminal. The voltage here I will denote that with VTH double prime. Now see, this is our total current I that is flowing for this current source. You will see this total current will be divided into two portions. One will go in this direction. Let's say I call this as I1. Another will go in this direction. Let's say I call this as I2. Now see, this I1 will flow in this direction. As this portion is an open circuit, you will see this I1 will return through this path, and here you will see this point and this point will be the same point. So I1 and I2 will get combined here, and I2 will, and total current I will return through this path. Now see, what is this VTH prime? See here, if this is our A terminal and this is our B terminal, see, I can expand this B terminal up to this point. So here you will see VTH double prime will be the voltage across this J2 inductive reactance and the resistance of 4 ohm. Therefore, if I redraw this circuit, I will get a new circuit like this, in which between A and B terminals I have to calculate VTH double prime, and here I have told you that this will be our total current I. It will be dividing into two portions. One will go through the 8 ohm resistor, I have denoted that with I2, and another will go into this branch. I have denoted that with I1. Now see, we have two parallel branches. One branch contains this resistance of 8 ohm, another contains the resistance of 1 ohm, 4 ohm, inductive reactance of J2, capacitive reactance of minus J3 in series. Let's say I denote this branch impedance with Z1. What will be Z1? Z1 will be 8 plus J0. Now see, what will be Z2? Here Z2 will be equal to 1 minus J3 plus 4 plus J2 equal to 5 minus J1. Now see, how do we calculate I1? I1 will be equal to Z1 divided by Z1 plus Z2 into total current I. I am using current divider rule. See, Z1 is only 8 divided by 8 plus 5 minus J1. I will multiply this with total current for phase angle minus 90 degree. This will be equal to 2.45. Phase angle will be minus 85.60 degree. Okay, this is our I1. Now see, VTH prime is the voltage across this terminal and this terminal, or VTH prime is the voltage across this 4 ohm and this minus J2 inductive reactance. I know the value of current that is flowing through this path, I1. I1 is entering from this direction, so this A terminal will be positive and this B terminal will be negative. So what will be our VTH double prime? I will simply take current I1 into the impedance from this point to this point, and that is equal to 4 plus J2, and our VTH double prime will be equal to 10.95. Phase angle will be equal to minus 59 degree. Here our VTH double prime is equal to 10.95. phase angle will be minus 59 degree. Okay, see here, VTH double prime, which has A terminal positive and B terminal negative. VTH double prime also has A terminal positive and B terminal negative. So as they are sharing same polarity, our VTH will be the phasor sum of VTH prime and VTH double prime. VTH prime and VTH double prime, 20 phase angle 0 degree plus 10.95 phase angle minus 59 degree. This will be equal to 27.3 with phase angle minus 20.1 degree. So if I want to draw the Thevenin equivalent circuit, our VTH is equal to 27.3 phase angle minus 20.1 degree, and our Thevenin impedance ZTH is equal to 3.18 plus J 0.71. okay, and that was across this A and B terminals, and this will be our Thevenin equivalent circuit. If I want to draw complete Thevenin equivalent circuit, I have to connect the load impedance ZL here. Okay, now see, if I want to draw Norton equivalent circuit, our Norton current IN will be equal to Thevenin voltage divided by Thevenin impedance. Thevenin voltage is 27.3, phase angle minus 20.1 degree, and ZTH is equal to 3.18 plus J0.71. So this will give us our Norton current IN equal to 8.389 with phase angle minus 32.69. So our Norton current will be IN, which will indicate 8.389 with phase angle minus 32.7 degree. That will be in parallel with Norton impedance. Numerically, the value of Norton impedance and Thevenin impedances will be equal, and Zn will be equal to 3.18 plus J0.71. If I connect the load impedance here, ZL, that will be our Norton circuit. Okay, that's it. Thank you.